Hello, my name is Rob Marsland. I'm president of Intraband LLC, and I'll be talking to you today about our Navy Phase 2 program called Lasers and Detectors for Free Space Communications in Adverse Weather Conditions. Intraband LLC, working together with the University of Wisconsin-Madison, has developed and patented new quantum cascade laser designs that maximize output power and efficiency in the mid-wave infrared from about 3 to 5 micron wavelength and the long-wave infrared from about 5 to 11 micron wavelength. These design approaches are based on the growth technology, metal organic chemical vapor deposition, or MOCVD, that is known to be most compatible with volume manufacturing and provides the best reliability. We presently have several research programs aimed at improving mid-wave IR and long-wave IR output power and efficiency, as well as developing new applications such as laser communications. Intraband has built up a laser and detector characterization facility that includes microwave frequency response as well as characterization of data transmission quality up to 12 gigabit per second. I should also mention that we recently presented our work on free space communication in the mid-wave IR at Photonics West 2024. The paper, published together with the University of Wisconsin-Madison, Naval Research Laboratory, Paravium Research, and DRS Daylight Solutions, was entitled Room Temperature Directly Modulated DFB QCLs and Resonant Cavity Infrared Detectors, RSIDs, for 5 gigabit per second on-off keyed free space mid-wave infrared atmospheric laser communications. The subject of our present Phase 2 program is to develop these components in the long-wave infrared region. The Navy's interest in this technology is driven by the ever-increasing need for secure, private, high-speed data communications between mobile platforms. Traditional radio frequency communications are not very directional and are relatively easy to detect, thus possibly revealing the transmitter location. Laser communication, on the other hand, can be highly directional. Wavelengths in the long-wave infrared correspond to the thermal emissions from room temperature objects, making them more difficult for an eavesdropper to distinguish from the background radiation. Optical communications also can't be jammed using RF radiation, making them ideal for noisy RF or RF-denied environments. However, for the laser communication link to be useful, it must provide adequate range and reliability while also providing the low latency of direct point-to-point communications. Laser communication systems in the shortwave infrared near 1.55 micron wavelength can suffer degradation due to turbulence, fog, haze, dust, and smoke. Although more data is needed, the long-wave infrared has been shown to perform much better in these difficult conditions. The research is still in early stages, so we need to meet the requirements we expect for future platforms and platform upgrades, such as to the Fire Scout UAV. The solicitation requirements translate into approximately 1 watt output power at 10 micron wavelength, less than 10 nanometer laser line width to allow for the receiver filtering, and better than 5 times 10 to the 9 centimeter root hertz per watt receiver detectivity while transmitting 1 gigabit per second in worst case conditions, but possibly up to 40 gigabit per second in the best case at low 10 to the minus 12 BER. The successful implementation of this technology will improve the operation of Navy platforms by providing data communication that does not have the vulnerabilities of RF, but works better than other optical technologies in adverse weather conditions. Most mobile platforms have a similar need. Our technology will help to achieve these improvements by providing much longer range, up to 17 times, in hazy or foggy conditions, while simultaneously making the communications harder to intercept. We are also working to improve the receiver side of the communication link to readily acquire the signal while rejecting background noise. We are developing distributed feedback quantum cascade lasers that will provide over 1 watt of average power while being modulated at speeds up to 10 gigabit per second and higher. We are still early in the program, but already we have fabricated lasers that produce 3.9 watt peak power under short pulse conditions. Here we see photomicrographs of the laser and detector we are developing. These microphotographs are actually from components fabricated in an earlier program that achieved 5 gigabit per second data transmission in the mid-wave infrared. We are doing a complete redesign to achieve even higher performance in the long-wave infrared, which is superior to the mid-wave infrared in adverse weather. The detector is called a resonant cavity infrared detector. The technology was originally demonstrated at Naval Research Labs at 4-micron wavelength. Here we are designing new detectors with the NRL to reach 10-micron wavelength. This slide shows the goals of our Phase 2 program. We've just completed the first year of the Phase 2 program, in which we focused on design of the DFB QCL and of the resonant cavity infrared detector. We were not able to grow any laser or detector material in the first year as we had originally intended because of availability of the MOCVD reactor as well as of the MBE system that is used for making the detector material. We showed these goals all as medium risk because of those issues of availability. We did, however, achieve our first goal, which is the 1 watt pulsed power DFB, which we achieved with existing material that we then formed into the laser for proof of principle. So in the second year of the program, we will grow the detector structure using molecular beam epitaxy, and we will grow the laser material by MOCVD and process the devices with goals of good quantum efficiency for the detectors. Here we're saying 1% quantum efficiency, which is for just the base material. But then once we form the detector cavity by transferring it onto another substrate, it makes it somewhat of a resonant cavity where we can get up to about 10% quantum efficiency just using the native reflection off of the detector material and a back gold mirror or silver mirror. We also plan to achieve 5 gigahertz modulation bandwidth with the quantum cascade laser. And then those working together should allow us to achieve at least 10 to the minus 9 BER at 1 gigabit per second. Then in our option period, if funded, we would move on to increase the laser power to 2 watts pulsed or half a watt CW minimum. And with that higher power, higher capability laser, we are forecasting that we would be able to reach 10 gigabit per second with good receiver sensitivity of minus 18 dBm and 10 to the minus 12 bit error rate. Here we see the key features, advantages, and benefits of the technologies developed under this program. So first of all, we're working on a laser that emits in the long-wave infrared at around 10 micron wavelength. The advantage is that this gives us up to 300 times lower loss in heavy fog and is less subject to turbulence and difficult to detect in the presence of a warm thermal background. The benefit is lower outage probability in weather, more covert transmission than radio, and less susceptibility to jamming in RFI. Achieving 1 watt output power from this long-wave infrared laser makes it easier to establish the link, since there will be more power available at the receiver, as well as a longer transmission distance. The benefit is fast pointing and alignment that enables the mobile application, where things are constantly moving and acquisition needs to be fast, and enables applications requiring longer range or higher reliability. The modulation bandwidth of the laser and the receiver bandwidth of the detector of up to 5 gigahertz, enables symbol transmission rates up to about 10 gigabaud, which could be 30 gigabit per second if you're using pulse amplitude modulation called PAM8, which gives you 3 bits per baud period. And the extra bandwidth can be used for transmitting overhead and thus reducing BR in difficult situations. The benefit is it enables the use in wireless front haul where very high data rate capabilities are needed. And the extra overhead can enhance the security and data integrity of the link if the extra bandwidth is used for that. The resonant cavity infrared detector that we are also developing under this program has an optical cavity that enhances the responsivity at a particular wavelength, but also reduces the responsivity at other wavelengths, providing an optical filtering function. This optical filtering function has the benefit of lower outage probability due to stray light or broadband jamming. It also gives lower cost because it has the built-in optical filter instead of adding that externally. The receiver quantum efficiency that we ultimately expect to achieve of up to 30% would allow longer transmission distance. And the benefit, of course, is to enable applications that require that range or just need the extra margin for higher reliability of the link. And finally, achieving the detector optical bandwidth, which is greater than 100 nanometers, means it'll be easier to align the wavelength of the transmitter with that of the detector, while still rejecting background noise outside of that 100 nanometer range. This requires, the benefit here is easier link setup and signal acquisition because it's easier to get the laser wavelength to hit the wavelength target there if the target is wide as 100 nanometers. The keys to transitioning this technology to the fleet is to find or develop a test bed that represents a relevant environment. Our operational improvement claims are based on published data, but more work is needed to prove the extent of the long-wave infrared communication advantage for specific Navy platforms. We also need funding to develop modules that are adapted to the test bed. Our aim is for this technology to be used to improve communications and communication security to UAV platforms such as the Fire Scout or platforms such as Advanced Hawkeye. In addition to the Navy applications, we think this technology could find wide application where low latency, high security communications are required and can't be served by fiber optics. For example, in 5G, 6G front haul, there's a need to connect a remote radio head to a base station. In situations where fiber is not practical and where the uptime of the laser link could be high, for example, in more arid climates where you don't get super dense fog, this application could be served by our system if we can get the data rate up to around 40 gigabit per second. We think this is possible with wavelength division multiplexing or by going to complex modulation, where we can send more bits per hertz, or possibly by increasing the bandwidth of the system. Another commercial application is LiDAR, where a laser is used to detect objects ahead of a vehicle. And this is a problem in the shortwave infrared, which can be blinded by fog and by other atmospheric conditions. We need better understanding of how the long-wave infrared performs in this situation with an imager to really understand the potential. Target customers for these applications include, of course, the defense prime contractors, but also the OEMs that serve the communication marketplace. My focus here is to meet new partners that can help us develop these applications. We will supply the quantum cascade laser on heatsink for new or existing programs. We would like to explore other applications requiring high mid-wave infrared power, such as infrared countermeasures, standoff chem biodetection, material processing marking, and other applications. We would like to expand our network of semiconductor manufacturing partners as well. Thank you for your interest in this presentation. If you'd like to talk more about this, please get in contact with me, Rob Marsland. My information is here on this slide. I'd love to talk more about your application or ways we can work together. Thank you.